this is from the top 500 list. So here we can see that this the first one, Jaguar, it has 224,000 cores. It consumes almost 7 megawatts of energy. At this point, it feels a bit bad when there has been presentation about how to save energy and be green. Okay, I'm thinking how to consume more and more and more to get more accurate calculation. But this is well, the other thing was that luckily there was mentioned that this raw resource is also important, because finding Higgs boson is, we don't know what to do with the information. We don't know what's the point of knowing what's the reason of mass. Okay, nobody knows what were the application for ARPANET. Suddenly somebody came and invited an application on the top of that, and rest was history. Well, interesting also here is that we find CSC from the position 65. Because of some reason, Sweden is a bit better, and we are desperately thinking how to correct this problem so that we could see Finland somewhere higher to consume more energy. Yeah, okay, now we come to this Forman solution to do petascale computing. So the idea is call it multiple expensive or expensive, depend how do you define what these expensive systems together. And these systems form a virtual computer. It's the same idea with the electric grid. So you really don't care where the electricity is coming as long as you are able to use your laptop. It's the same thing with calculation. You don't care who is solving your problem. For example, how many of you know where is the web server of Helsingin Sanomat? Or do you even care about that one? You care that you get the information that you are looking for. It's the same thing for us with the calculation. So in principle, I don't care who solved or whose hardware is, and definitely I don't care who is paying the electricity bill. But I do want to have the answer. And in this academic world, we are using grid middleware to collect these resources together. And here I have mentioned some of those. So OpenScience Grid is used in States, ARC is used in Nordic, and G-Lite, for example, at CERN. And here I have two different definitions what grid is. For non-technical, well, first is technical persons, we could say that's a global batch queue system. You submit your job and you get your answer at some point. For those of you who are not so technical, so we could say that grid is a postman that delivers your postcard from your holiday to your friends. So you write the postcard your address where it is, where it's supposed to go, and you write your greetings, hello from this sunny beach here, and have a nice rain at Finland, something like that. And the simplified picture about this is that you write your task, for example, your analysis task. I want to use that data set to find this event at that point of time. You define those, you log in to grid, you send your job, and at some point you get your answer back. A bit more technical how it works, how we collect these resources together, is that here at the bottom of the image we have the user, and then we have some kind of resource broker. As we have DNS service in internet world, this resource broker knows about what kind of resources we have around the specific area. It could be around the globe, or it could be around the Nordic, or some other place. So when I send my job, I first send that to the resource broker. The broker checks, okay, you want to do these things using that data set. It checks where the data is located, sends my job there. The job is calculated on the resource, and then when it is ready, the result is sent back to me. So, in practice, it is so trivial to do petascale computing with inexpensive hardware. Now we take a look at this top 500 list, and we add this our grid system here. So when we calculate these together, we see that we get more than 1,000 computing cores. At this point, it doesn't make sense to calculate how much we have spent money to develop middleware and how much we have spent money to all other things. But the idea is that with the small systems, when we collect those together, we are able to get a bigger system. And for example, in our case, we are able to use this system to solve this problem. What's the reason of mass? And this is what we have in Finland. So from this network point of view, we have 10 gig line to Denmark, and from Denmark the line is going to CERN, and the data is coming from there via Denmark to Finland, where we store it and analyze it. And at the moment we don't have any massive huge computer somewhere sitting and waiting. We have plenty of small ones around. So we are using the same idea that I showed you in the global scale. So we are doing the same thing in Finland. So we have something at Innopoli, we have something on the premises of CSC wherever they are, and something at University of Helsinki, at Kumpula, and also in Jyväskylä. So when we collect all of these, we get pretty okay system. So, summary. Petascale computing is already here. As you see, either you go and buy directly a big computer if you have money, or if you are poor like us, so you collect plenty of small ones together and use that as a big virtual system. There are some problems, unfortunately. So the system what we have in Southern Europe and the system what we have in Nordic, so in paper they interoperate perfectly. In practice, there are small things that has to be ironed out. But if there wouldn't be, I wouldn't have a job. So it's good to me that there are challenges. Okay, so this is my presentation. Here's our latest system that has been cabled on Tuesday. It has about 700 computing cores, and believe that the Higgs boson is going to find using this system.